So finally we have come to our last assignment problem today. So we'll try to stick to the timelines what you are suggesting, sir. But at the same time, we'll try to do the justice on the topic. So before we move on to the question which was asked, why can spacecraft hover in space without orbiting a planet? In the context of Lagrange points and hello orbits, and our problem is three-body problem. But before we go to this topic, again, like I've been doing, I want to give a big picture that what is this problem all about. So first I'll start with very basic problem where there is a person who is moving with a moving train which is moving at a constant velocity v0. So if he throws a stone, if he just drops a stone, what will be the motion as seen by a person who is sitting in the train, and what will be the motion as seen by a person who is moving with the train? And all of us know that from classical mechanics, the motion as seen by the person who is standing outside will be a parabolic motion, and the person who is observing the motion, who is moving with the train, he will see that the stone simply falls down. Now both the descriptions are correct. It is just a matter of which reference frames you choose. So my motion description, my physics, actually the nature of equation changes once we change my reference frame. And that is all because in this reference frame there is a horizontal component from the ground frame which is no force is there to cancel that out, and that's why we see a parabolic path. And this exact analogy can be taken to a sun-earth system and a satellite system which is placed here. So we all of us know that our entire Milky Way galaxy, our entire Milky Way galaxy is moving through the entire universe at a huge bulk speed, and our solar system does that. Sun has that velocity of roughly about 220 km per second, and also Earth orbits the entire thing. But do we see those motions? But do we really see those bulk motions? That is not because it is not there. That is because we are observing from a frame, say a satellite or say from the Earth, which is actually moving or having the same bulk motion as the entire galactic motion of the entire system. And that is the reason why this picture is only valid from the reference frame, which is basically moving with the sun-earth system along with the galaxy. So the problem what has been given, actually it is a problem of a reference frame. That means, truly speaking, if there is a true inertial frame, the entire motion of our solar system is actually a chaotic motion. It will travel at huge bulk speeds and a lot of chaosness will be there. But the moment we see this from a nearby observations which are moving along with the systems, moving with the sun-earth system, we only see the relative motion what is happening, and instead of that we don't see what is happening at the bulk galactic motion. And this problem are effectively the problem of reference frame. So the question, why can spacecraft can hover in space without a planet, is actually mathematically a problem of reference frame. And this entire Lagrange points and halo orbits, and this question can only be explained if we move on to a frame which is basically moving with the sun-earth system, and which is essentially a rotating non-inertial frame. And this question makes the sense when we stick our observation from this frame of reference. And all of us know that when we observe a body's acceleration, say for example there's a spacecraft or any body in a we'll come to three-body understanding just for sake of understanding. If there is a body, then the acceleration felt by the body from the true inertial frame will only be having the inertial acceleration which is coming from the real forces. There is no fictitious forces as seen from a true inertial frame. But the moment we observe this points dynamic from a rotating frame, these complicated terms will come, and because lack of the timing, this is a very elegant equation which I want to derive, but it's okay. All of us know that it is basically having three components. One is the component of acceleration. If the point is moving relative to this frame, it is that component. It is something having called Coriolis component, and it is something having called centrifugal component. So it is very inherent that the moment we look from this frame of reference, these forces are going to come. So what actually happens if we just go through our slides? There are so many paradoxes which can be explained through this Lagrange point and all that. So actually, just before going to this one, I just want to point out on the ideas of Lagrange points and the halo orbits. They are actually, truly speaking, they are not stationary points in the space. They are actually, because these points are nothing but mathematically these points are located at five locations, and this entire picture is actually moving in the space. And that is the reason why if observed from a true inertial frame, these points will not be a fixed point in the space. It is only fixed in the reference of this rotating frame. And then these 5 points become a such points with reference to this image where the net forces is basically 0. So all these points are basically the solution of this equation. If you plug in the conditions which my teammates will do, how these points are coming as a part of the solution of this kinematic equation, we'll find that these points are the 5 solution points when this equation will be satisfied in some way or the other. So basically what happens, the gravitational force is equally balanced by the centrifugal force of due to the 50 ts force which is coming from the frame of reference. So we need to understand before we discuss this question that whatever we are seeing, it is from a frame of reference which is a rotating frame of reference, and that's why we only see the relative motion from that frame of reference, and we don't see the bulk galactic motion what it is. So that is the reason why this problem is nothing but a problem of reference frame, and which gives the idea of Lagrange points and halo orbits, which will be coming in the coming slides, and this is how we should understand pictorially. Now the only thing which I want to add here is that these Lagrange points are 5 points, but as we know that these are equilibrium points. We'll show that the net forces in this picture only, the net forces is equal to 0 at those 5 points, and we know from the physics that equilibrium point can be a stable equilibrium point and can be an unstable equilibrium point. So these 5 points turn out to be unstable equilibrium point, which can be brought out from the linearized dynamics, which will be covered in this one. So basically any perturbation can be any perturbation delta x from this equilibrium point, any perturbation from these equilibrium points can be, for small perturbation, can be captured by the state dynamics in this way. And it is actually found that for these 3 points, the eigenvalues of this A matrix coming from the A matrix is actually unstable values. That means the linear stability says that these points are actually unstable points, and these 2 points are actually stable points, and there is a lot of history behind this which will be covered. And but the point is, these points are basically some equilibrium points, and we know that the actual 3-body problem or the restricted 3-body problem is a nonlinear equation. So though the linear stability, so the linear dynamics shows the unstable nature of these points, but actually what happened, due to the nonlinear nature, this instability becomes a kind of an orbit. That's a 3D orbit around these points. So it appears that if there is a spacecraft when we observe from this rotating frame of reference, it appears that this spacecraft is actually rotating about or orbiting about this point. So that is the reason why our topic actually that gives us, why can spacecraft hover a space without orbiting a planet. So this is the reason why this is the orbit which is coming from the mathematics, that how a spacecraft can orbit a point instead of orbiting a planet. So this is the big picture which I wanted to give, and the corresponding slides and the content will be just the mathematical ideas and more abstract ideas in terms of how to understand instability and how the solutions evolve from these unstable equilibrium positions. So I'll just run through these slides. So just the astronaut paradox. If there is an astronaut sitting at the L1 Lagrange point, and we know that at this point there is a perfect equilibrium from the rotating frame of reference, there is no velocity, no acceleration, but there is a paradox that if it takes a breath, even it imparts a very microscopic delta V, the entire system shows from the linear instability that the system will diverge from that position and cannot come back. So this is a paradox. So the core question is, if gravitational centrifugal forces are perfectly balanced here, why is the breath fatal? That is because this understanding is from the linear dynamics. The more profound understanding will come from the nonlinear dynamics. So once it moves from that equilibrium point, it actually settles into a 3D halo orbit, which is essentially a 3D solution of the nonlinear dynamics from the unstable positions. And there is a huge chunk of history which talks about how this started, and since the telescope era, when Galileo and Kepler mapped the solar system, they didn't find any sort of points which are basically static in our nearby solar system, and so at that time there was nothing to prove that yes, there are some points where the points are the reasons where nothing is moving, because the rule of gravity says that everywhere they looked, they observed exact same phenomena. Gravity demands motion. So the question was, did anyone observe a star, planet or a rock hovering perfectly in a deep space? So these questions were actually there in the history, and many people right from the Newton tried to solve this problem, and Newton was very successful in describing the 2-body problem, where the maths gave clean predictable ellipses. But the moment he took a 3-body problem, which essentially means there are 3 masses and each mass can actually affect the other mass. For example, the sun, moon and the earth. If we take the masses of these three celestial objects, they can actually they can actually, affect each other's motion. So if you try to really solve this problem, there is no analytical solution for a general three-body problem. And this is the reason why Newton had reportedly told his friend that he was getting headache and he was not able to sleep in the night because he was unable to solve the equation for the moon, because that is affected by both sun and earth, but in a very highly nonlinear manner. And then came the Euler, who actually brought out the idea of the circular restricted three-body problem, which actually meant that one of the bodies from the three-body system can be a negligible mass, such that that mass is unable to affect the other mass's motion, and thereby we can simplify the mathematics. And whatever this picture has been shown, it is actually a result of the three-body restricted problem, which Euler initially found. And then Euler actually found these 3 points, and Lagrange, whose student, pushed his work, and he found further 2 points. But till this point, everything was mathematical. Nothing was actually observed in the real space, that there's something called such points in the space. And then finally 1906, after 134-year-old wait, eventually they observed something which is known as 588 Archelaus, to see that in around the Jupiter and Sun system, they indeed have some places where they could find that it was locked in the empty space, permanently leading. That means there were asteroids which were actually not moving around the sun in a normal fashion, but actually they were locked in the empty space, permanently leading the Jupiter by 60 degrees. So this actually validated whatever the mathematical findings of the Euler and Lagrange, what has come after that. And as I explained, these L4 and L5 points are highly stable points, which will be explained like in the further slides. And that is the reason why any perturbation, they don't go into kind of an orbit, rather they still stay there. And that is the reason why in regions around L4 and L5 of Jupiter Sun system, we see a lot of asteroids and comets actually sitting there silently, not moving from a rotating frame of reference. And there are many such cases in our galaxies where we find these L1, L4 things, which is like for example, we have this kind of Scorpius case studies and these observations, which tell that yes, these are indeed not mathematical points, but yes, there are actually in the reality there are points which behave like that. But of course, there is a huge mathematical simplification that the third body has to be a negligible mass body. And then the recent humanity exploiting these things was our own ISRO's mission Aditya L1, which is actually, it is orbiting around the L1, in the orbit around L1, and the James Webb telescope, which is used to really see the universe, it is orbiting around an halo orbit in L2. So we are exploiting, the humanity is exploiting, and the L3 orbit is actually not feasible to be exploited. And this is basically how the history has evolved through these things, from a general three-body system to a restricted three-body system, and how this is being used in in our engineering missions till now. So further will be taken care by Yash, who will be explaining the mathematics behind the ideas.
Yes, so we, from Gaurav's perspective, we know the big picture about our presentation. So we start with one mythology. So there is one story before Ramayana. स्टोरी ऐसी है, लॉर्ड राम के एंसेस्टर थे किंग त्रिशंकु. लॉर्ड त्रिशंकु का जब वो राजा थे, बहुत ही अच्छा काम किया उन्होंने. सो वन डे उनको ये हुआ कि मेरे को हेवन में जाना है, बट इन माई मोर्टल बॉडी, सो मुझे मेरी सोल नहीं जाना चाहिए, एज अ होल मेरा बॉडी वहाँ पे मेरे को जाना है. सो उन्होंने बात किया वशिष्ठ, उनके गुरु वशिष्ठ से बात किया, बट वशिष्ठ ने उन्होंने ऐसा बोला कि दिस इज़ द अगेंस्ट द लॉ ऑफ नेचर. सो वो बहुत ही गुस्सा हो गए, और उनके 100th सन जो थे उनसे उसने बात किया. उनके सन भी इतना गुस्सा हो गए कि जिससे उनको एक श्राप दिया, जो श्राप की वजह से वो बन गए चंडाला. चंडाला बनने के बाद वो जंगल में भटकते रहे और वहाँ से वो मिले गुरु विश्वामित्र से। जब उन्होंने ये बात किया कि गुरु वशिष्ठ ने उनके साथ ऐसा किया, और विश्वामित्र का पहले से ही एक अनबन चल रहा था गुरु वशिष्ठ के साथ, कि जिसकी वजह से विश्वामित्र भी उतने ही बड़े थे जितने गुरु वशिष्ठ थे, बट कभी उनको मौका नहीं मिला था उनकी पावर दिखाने का। सो उन्होंने ये टाइम का एक यूज़ किया और उन्होंने किंग को बोला कि मैं तुमको भेजूंगा हेवन में बाय यूजिंग माय तपश्चर्या। तो एट दैट टाइम उन्होंने उनके यज्ञ किया। यज्ञ में उन्होंने उनका पूरा पावर लगा दिया और किंग त्रिशंकु को हेवन के गेट तक उन्होंने पहुंचा दिया। जब वो एंटर करने वाले थे तब गॉड इंद्रा को पता चला कि ये एक मॉर्टल बॉडी वहाँ पे एंटर कर रही है, जिसकी वजह से पूरा का पूरा जो हेवन है उसके जो अलाउ नहीं करता है। सो इंद्रा ने गुस्से में आके उनको वापस से बैकफायर किया। सो जिस टाइम पे वो गिर रहे थे किंग त्रिशंकु, तो उन्होंने चिल्ला के बोला विश्वामित्र को कि मुझे बचाए, मैं अर्थ के पर मैं गिरने वाला। उस टाइम पे उन्होंने स्टॉप, सो इन संस्कृत वर्ड है जिससे उन्होंने स्टॉप वर्ड यूज़ किया, जिसकी वजह से उनका जो वर्ड का जो पावर था और इंदिरा का उस टाइम पे जो पावर था वो दोनों सिमिलर हो गए और वो एक स्टेबल पॉइंट पे वहाँ पे पहुँच गए, जिसका नाम हुआ त्रिशंकु हेवन। तो उसके बाद विश्वामित्र ने उनका पूरा पावर लगा दिया, वहाँ पे एक पैरेलल यूनिवर्स बनाया जो अगेंस्ट द लॉ ऑफ नेचर जा रहा था। सो इसलिए इंद्र भगवान आए, उनसे बात किया और वहाँ से उन्होंने ऐसा डिसाइड किया कि त्रिशंकु को हम हेवन में तो नहीं ले जा सकते, बट हम ये जो आप जो स्पेस बनाया है उसको हम वहाँ पे आए वो परमानेंट रख देंगे। सो दिस स्पेस इज ऑलरेडी देयर। इफ यू सी ऑन साउदर्न नॉर्दर्न स्फीयर इन, so if we see one of the celestials, it's called crux. So crux एक सेम वे में दिखता है जो अपसाइड डाउन दिखता है, और बाय आर माइथोलॉजी वो एज पर माइथोलॉजी इट्स लुक लाइक त्रिशंकु हेवन। सो त्रिशंकु हेवन के से हम रिलेट कर सकते हैं कि इट्स लाइक दोनों के पावर्स, यहाँ पे सन और अर्थ का ग्रेविटेशनल पुल के वजह से वहाँ पे कैंसल आउट होता है, यहाँ पे विश्वामित्र और इंद्र के पावर की वजह से वहाँ पे कैंसल आउट होता है और वहाँ पे त्रिशंकु हेवन बना। द सेकेंड थिंग इज द आर्यभट्टा। सो वन ऑफ द one story we know that Newton and Euler has found their inertial frame and rotating frame, but it's already found by our own engineer Aryabhatta. So at the time of 5th century, Aryabhatta observed that by just observing a star. So star is going from east to west. So by that logic they come up with that the earth is rotating. So because we are in a rotating frame, due to which the star, we can see the star came from earth east to west. From that analogy, we first came up with the reference idea, what is the inertial and what is the rotating frame. Now we start with our inertial frame. So if we just see our universe from a deep space where we are just standing there, so everything is moving with respect to other thing. So one galaxy moving with another galaxy, one planet is moving with another planet, and the moon is orbiting around the planets. So from that perspective, everything is rotating. So we can't able to see that any hovering kind of concept. So from that concept, we came up with the synodic hack. So what is the synodic hack? Synodic means the rotating frame. So Euler came up with this idea that if we analyze our system rather than from inertial frame, by just shifting from the rotational frame, we can see some of the points. Some of the points we can see or not, we will prove that, but they come up with the concept of a rotating frame. So from rotating frame, if we just assume that there is an hovering object which is lie between a sun and earth, so to prove this, we have to still use a Newton's law. What Newton's law tells that whatever the initial tendency of the object remains in that path only. So in a orbital plane, from inertial frame of reference, uh, it just the whatever object is there, it just follows the tangential part of the orbit, but due to the centripetal force, it will rotating around the orbit. To mimic that the same phenomena in a rotating frame, they come up with the two fictitious forces. One is the centrifugal force, one is the Coriolis force. So the centrifugal forces came because we are sitting on a rotating frame. So from the our rotating frame of perspective, we feel that if we just take a one circle, and if we just stand here at this circle, and this part is rotating at a constant omega. So if we see in our rotating frame of reference, we feel that the floor is pushing on us, and we feel our fictitious force that we are also pushing the floor. So it's feel like a fictitious gravitational force which is pulling you out of the frame, and the whatever metal part is there which is pushing you inward. So due to which the equilibrium point we came up, and this force we called is the centrifugal force. The second is the Coriolis force. For the Coriolis force, what we see that we are in a rotating frame. If I threw a ball, so it's feel like it's going in a curve path, but in actual reality, from the inertial frame, it's just following the straight path. But due to our mind is not tweaked like a rotational frame, it just observe in a inertial frame, due to which this fictitious phenomena of curving the path we can able to see. To see that by one experiment which is done in one of the MIT professor. So just give me 1 second. One second, sir. फुल स्क्रीन के लिए क्या है? यूट्यूब पे करना पड़ेगा,
डुप्लीकेट करना पड़ेगा स्क्रीन डुप्लीकेट करना पड़ेगा।
1 सेकंड सर,
लास्ट में दिखाता हूँ,
कर देता हूँ।
अरे विंडोज़ पी कर, विंडोज़ पी डुप्लीकेट।
Yeah. So if you just see from our inertial frame of reference, it's just rotating. Yes, sir. So that the centripetal force. And this from a rotational frame of reference. So that fictitious force is filled by the string, so that's why it's taught while rotation. and the second is the Coriolis force. So yeah. So if you see from rotating frame, it's feel like a curve. Yeah. So if you see on a inertial frame, it's just on a straight path. Yeah. So now we will start with the derivation of the three body problem. So as Gaurav sir said that we have restricted from a purely three body problem to a circular restricted three body problem. So in which what we have, first of all we have assumed that the third body mass is the negligible. The two primary mass has the property of m1 is greater than or equal to m2. Let's say the mass 1 is the mass of sun and the second mass is the mass of moon. The second assumption for this that uh, the the gravitational perturbation created by the third body, which we have assumed that it has a negligible mass, it will not perturb the mass 1 gravitational field or the mass 2 gravitational field. And the second assumption, second thing we have done this, whatever we are observing our dynamics, it's perspective of the barycenter. So what is the barycenter? Let's say take object 1 and 2. Mass 1 it's our sun, mass 2 is earth. So if we take this as a take as a system, so the center of mass will lie at some point which we will call a barycenter. So what we have done is that whatever the reference frame is there, we have put our reference frame at the center of mass, and we have assumed that the center the rotating frame is rotating at a constant angular velocity. Second is the orbit, whatever orbit is, it's a circular. In real life we know that earth is not purely a circular orbit, it's an ellipse orbit, but the eccentricity is so much small that we can assume that it's a circular orbit for a first iteration. The second is the barycenter point. So barycenter point is not outside of the sun, but it's far more near to the sun center of mass, due to which we never feel that the sun is sun is rotating about some point, but its distance is so much small that we never feel. But we can feel if we take a Jupiter instead of Earth, then the barycenter is came out from the sun sphere, and so in that case we can able to see that the sun is also orbiting around that barycenter, and Jupiter is also orbiting around that center. Second is we are doing a non-dimensionalizing. So why we require a non-dimensionalizing of any equation? From fluid mechanics we know that if we non-dimensionalize some quantity, it's easier to analyze the point. Let's say we are dimensioning force, we call it a Reynolds number. So we know that from Reynolds number we came up with so much theories and all. So in that case also we are normalizing such a way that the total mass is m1 plus m2 equal to 1, the distance between the sun and earth is 1, the universal gravitational constant value is 1, and the system angular velocity is 1. So from this perspective, if we put this mass m1 equal to m2, m1 plus m2 equal to 1, and if we have to normalize this mass, so let's assume that m2 equal to some mass ratio mu. which is m2 upon m1 plus m2. Put this into this equation, we get m1 equal to 1 minus mu. As we already discussed about barycenter point, so we'll start with our derivation. It's not a simple derivation like a two body problem. So this is sun, this is earth, center of mass, and we assume that the third mass, let's say spacecraft is here in a three-dimensional space. Distance is r. Distance from barycenter is x1. For earth it's x2. Now we find first the center of mass. So what is center of mass is m1 x1 plus m2 x2 upon m1 plus m2. We have put our coordinate system such a way that the origin of the coordinate system is exactly lie upon a barycenter. So this point is 0 0. Put right side 0 equal to this. So we come up with m1 x1 plus m2 x2 is equal to 0. Now we'll put m1 and m2 values, which is 1 minus mu and mu. So from this we'll get our equation x1 in terms of mu, x2 will become 1 minus mu, which is our new non-dimensionalized coordinate system. Now we'll define a spacecraft location. So for finding a spacecraft location, what we do? Sun, moon, and let's say this is a spacecraft. The distance is r1 from mass 1, r2 from mass 2. From barycenter, its distance is r. To finding r1, it just r1 is equal to under root x plus mu square plus y square plus z square, and r2 will become x minus 1 minus mu square plus y square plus z square. So now we come up with all the requirements of r1, r2 and the non-dimensionalized quantities. From there we start finding our acceleration. So from video we see that if we have to truly generalize our system with respect to inertial frame and the rotating frame, what we can do? We define a two frame of reference. First is the ground, which is our inertial, and the other is T, let's say table, which is our rotating frame. So for both we define this dr by dt is equal to v and dr by dt v in a frame of reference g and t. From this frame of reference we come up with the velocity in g frame is equal to velocity in t frame plus omega cross r. Omega cross r will take care about the rotation part, and the velocity with respect to the frame t will take care about the motion in a t frame. From this, if we take derivative of this and we just put algebra, then we can come up with this equation, which is a of g equal to a of t plus g d omega by dt cross r plus 2 omega cross r in t frame plus omega cross r. So this is the Coriolis part, this is centrifugal part, this is d omega dt with respect to in a G frame, which is experience this is the rotation of T frame by experiencing in a G frame. This is the acceleration T, and this is the general inertial frame of the acceleration in inertial frame of reference. So from this we try to get rid of some of the equations. So for that we use our first assumption that omega is unity. So omega is 1. To apply this in Coriolis part, put omega 1 in Coriolis and the centrifugal part, put r value also into Coriolis and the centrifugal part, and also the value of v. We come up with these equations, which is ax, ay, az, which is x double dot minus 2y dot minus x, ay will become y double dot plus 2x dot minus y, and az become z double dot. Now we will introduce the gravitational force, which is experienced by the mass m1 and mass m2. So what is that acceleration force? Which is a unit mass. So it's become 1 minus mu upon r1 cube r1 minus mu upon r2 cube r2. So mu is m2 and 1 minus mu is m1. So from this we come up with our acceleration value, which is in general acceleration value. Take a 3 components of this, put this in a previous equation. So the final equation we'll get is the similar to this, gx, gy, and yeah. So we'll come up with this equation. Now what we can do, if you see in a right side part, this is just a vector quantity. So to define any vector quantity, we can do a scalar field. So what we can do, define a scalar field u such a way that we can convert it to a vector. So in a streamline derivation, we all know that we have introduced one vector called u, and just do a grade of u, it will become a vector. So we have to make this grade u type of term. To make this grade u term, what we can do, we take any function of u equal to x, y, z, and assume that u equal to x, y, z is it is the same term. We just assume that u is equal to this. From this we integrate this term with respect to x. So from after doing the integration with respect to s, we come up with one formula, which is f of y and z. Why we came up with not constant but a function? Because it's a partial integration. Again we do a del u by del y. From that we came up with another constant gz. Again we do a del u by del z. From that we come up with the zz value equal to c, and we know that it's feel like a potential energy. So what is the minimum potential energy? It's equal to 0. So we put c equal to 0, and for the final equation, we come up with this. So after doing this all of the thing, we make a u function. Just take a del u by del x, which is equivalent to the term, and same for del u by del y will become the similar term for y double dot. In this expression, we have not put any z equation. So z equation will be yeah. So will become a z double dot equal to del u by del z. Now what we do, from our initial condition, we know that it's a hovering problem in a rotating frame. So there is no velocity, there is no acceleration. So x dot y dot z dot will become 0, x double dot y double dot z double dot will become 0. So if we put 0 term into this equation, del u by del x becomes 0, del u by del y becomes 0, del u by del z becomes 0. Again we put del u by del z equal to 0 here. So it's become z double dot equal to 0. The formula of z double dot is minus z in bracket 1 minus mu upon r1 cube plus mu upon r2 cube is become equal to 0. The bracket term will always remain positive. So from this equation we come up with z equal to 0. That's why it's called a planar problem, not a 3D problem. Then what we'll do, we take take the second equation. If we put del u by del y equal to 0 and put y double dot and x dot equation into this, we come up with this equation y in bracket 1 minus mu upon r1 cube minus mu upon r2 cube equal to 0. From this equation, what we can do, either y will become 0 or the bracket term will become 0. So we have two conditions, y equal to 0 and y is not equal to 0. For y equal to 0, we come up with L1, L2 and L3 point, which is yeah. So we can see that we have two cases, y is not equal to 0, y is equal to 0. So from y equal to 0, we come up with 3 L1, L2, L3 point. So it's not a simple way like we come up with only 3 roots. So when we put y equal to 0 and z equal to 0 in del u by del x term, from there we come up with a 5th order equation. If we put a del u by del x equal to 0, this is x minus 1 minus mu x plus mu upon x plus mu q mu x minus 1 plus mu upon x minus 1 plus mu q equal to 0. So from this equation we come up with 3 conditions, which the 3 conditions is like this. First is minus mu x 1 minus mu. So from this condition r1 become x plus mu, r2 become 1 minus mu minus x, which we assume that it's a gamma. So from this, after putting all of this, we came up with a 5th order equation, and to find the 5th order equation, it's not the simple way. So we have used a Newton-Raphson method. From Newton-Raphson method, we come up with 5 roots. 4 roots are complex roots, imaginary roots, and 5th one is the real one. So from we know that gamma is the real quantity because it's came from the distance. So the imaginary part is not make any sense. So from that we came up with the L1 point, and if we take 2 other conditions like x is greater than 1 minus mu, we come up with the L2 point, and x is less than minus mu, we come up with the L3 point. After that we start with if y is not equal to 0, so we come up with the special condition. If we take r1 and r2 equal to 1, so it make a equilateral triangle which is 60 degree apart at above the horizontal line and below the horizontal line, from where we come up with L4 and L5 point. So by this, why we have gone through this derivation? Because at that time there is no method called state space representation, which will be derived by Anirav. So so they do this rigorously by their hand and come up with 5 points, which is 5 Lagrange points. It's not talk about stability, so we just came up with only a 5 points. But after this slide, we start deriving by using a state space representative, from where we came up with the stability of all of these 5 points. So now Nirav will continue.
Thank you. Good morning, myself Nirav. Good afternoon. Very bad, very bad. So yeah, my mind is fried by all these tedious mathematics. So conclusively, I would try to conclude what all those mathematics was about. So eventually, what we got is we got some equilibrium points in the space, and for engineers, the moment an engineer sees an equilibrium point, the first question that comes to mind is whether if it is a stable equilibrium or it is an unstable equilibrium. This is the first question. So चुल मचती है हमारे कि यार ये तो देखना है. So for to analyze that, we need a state space representation, and what is this and how this exactly works. We assume a linear domain in which we say that let's deviate our spacecraft slightly from the equilibrium point and see how the deviation grows or how the deviation reacts and with time. So we represent eventually our state space representation is written like this: x dot is a function of delta x delta y, and speed and the uh, displacement, the change in a small change in displacement and speed. So if we analyze this using all the mathematics that just derived by Yash, we get a 4-degree equation in the eigenspace. So we get 4 eigenvalues for this system, and what we found that for the points L1, L2 and L3, there is at least one eigenvalue which is positive. So from this equation, the nature of solution is like this: e to the power lambda times t. So if any eigenvalue that is lambda is positive, the solution will grow with time exponentially, which is an unstable. But not all of the eigenvalues are positive. Some eigenvalues are strictly imaginary on the imaginary axis, and some eigenvalues are stable also. So what this gives is, this gives a geometry of kind of a saddle point. So what this slide is telling us that the geometry of the system on some axis is stable, and while on other axis it is unstable. See, on this axis it is kind of unstable, which is due to this Coriolis force, and on this axis this is a stable axis. So we can maneuver around this equilibrium point, but yeah, let's see what we have to do that. So the points L4 and L5 on the other side are stable, but require some constraint in order to become really stable points. Yeah. So we derived that the geometry of this system is like a saddle point. So what exactly we mean by that, and what we get from this is a halo orbit, which is a 3D orbit, which is nothing but when we try to derive all those things using the linear mathematics, we cannot do it, because as the deviation grows exponentially, as the linear assumption fails here, and we require some non-linear mathematics in order to exactly derive the shape of the non-linear orbits and all. So when we derive that, we get some kind of a halo orbit, which is a 3D orbit in which, due to non-linear coupling only, it is a kind of a stable orbit, which can place a spacecraft in a confined space, because it is very special and it is very important, because in systems like these, systems where the non-linearity can overtake any time, the systems are very chaotic. As stated by the mathematician Poincare, he studied chaotic systems, and what he concluded that in studying these chaotic systems, the initial conditions are very much important. So initial conditions are a key thing in these systems, because a small deviation in initial condition can cause the system from go to stable to a chaotic, and cause the system to go beyond our imagination. We cannot predict that motion and all. So in order to keep our spacecraft in a particular halo orbit kind of like, we as I said earlier, it is a saddle geometry. So if we require our spacecraft in a one axis only to move periodically, we require continuous station keeping. What is station keeping means is, we don't want a spacecraft to move in the perpendicular axis, because the perpendicular axis is unstable. So in order to prevent that, we need constant thrusters and constant monitoring to keep our spacecraft in that axis, which is the stable one. So this is just for respecting all the mathematics that was done by the Euler, Lagrange, and Yash. So yeah, the all the tedious mathematics was done just to identify the equilibrium points only. So we need something more. We need something to analyze the nonlinear systems. We need something to analyze the eigenvalues and all. So we need to introduce the Jacobian matrix and all, in order to see what orbits are stable, what orbits are unstable, and what orbits are periodic. Basically, if we get imaginary here, if we get imaginary eigenvalue, the solution would be periodic. So if these L1, L2, and L3 points are unstable, why would we need to go there? Because it is it is unstable. It can be unpredictable at if things go slightly wrong. So why exactly do we need to stay there? The speciality about L1 point is, it constantly faces the sun. So, and the speciality of L2 point is, it is in very deep space, and we can get such type of observations which we normally cannot get. So we also need to go there, but it is unstable. So what is the solution here? What is the escape? So the escape is here the non-linear escape. We cannot keep we cannot keep relying on linear analysis. We cannot keep relying on linear Jacobian matrix analysis and all, because this is fine just to derive what what directions give nonlinearity, but it cannot characterize, or it cannot further analyze the nonlinear motions, because this assumption fails as the motion goes forward, as the deviation grows with time. So we need nonlinear mathematics in order to analyze the orbits such as the halo orbits and all. So yeah, this halo orbit is perfect example of how beautiful a nonlinear motion can be. So this happens when the two oscillatory modes, when we derived earlier, we got four eigenvalues. So there are two imaginary modes which represents the oscillatory mode, which are perpendicular to each other. But the beautiful thing happens when the two oscillatory modes frequencies match with each other. We get a perfect synchronous orbit like halo orbits, and which is what exactly or JWST uses in order to hover the L2 point. Finally, this is what I've been. If those perpendicular frequencies doesn't match, the orbit can go very chaotic, and it is not very useful to us. But if we somehow place the spacecraft far enough, so just at the point where the omega xy and omega z matches with each other, we get a beautiful orbits like halo orbit and all. So my conclusion here is, we need linear analysis, we need all the linear mathematics just to analyze, but it was historical, it was traditional methods. Now we have modern computers and all, we can do nonlinear analysis and all, we can operate on such kind of orbits in order to exploit more in deep space and all. So yeah, next Bharat will continue.
Hello everyone, myself Bharat Kumar. Yeah, so we find halo orbits in the Lagrange point, and we simply can't place them. There are some problems and realities and for solutions. The halo orbits exist, but they are very unstable, unstable linear manifolds. And the reality is, because of the disturbances, even a small disturbance, it can, because of unstable, even the small disturbance can drift it away. So we have, the solution is station keeping. We have to always maintain the satellite in that orbit. Station keeping is important, like giving the thrust occasionally, and yeah, it is like a paying tax for that. Yeah, the invariant manifolds. Uh, because these Lagrange points exist, there is a stable and unstable manifolds at the same point. These fields will create the invariant manifolds, which we can use for traveling to the, opening the gates and jumping from one orbit to other orbit in another orbit of the space. How this exists, I will explain. As we see, this is sun and this was earth. Lagrange point will exist somewhere here. So because the gravity of earth is acting like this and sun is acting like this, if you look at the 3D point of view, at that exact Lagrange point, the forces will be acting like this, and other will act like this. Because if we take the orbit, this is orbit of that Lagrange point, how it moves. Take this as a y-axis, and this one as x-axis, and z-axis to the board. Uh, because the gravity is more here, where the sun and earth are near to the Lagrange point, they are pulling each other. Whenever the object goes this side or above or below, it will attract towards that point. So if you look at a 3D point of view, this is y-axis and this is x-axis, and above z-axis, it is also points towards the Lagrange point. See, along the x-axis it is pulling, and all other axis it is pushing to the Lagrange point. So this will create, whenever whenever we want a like any satellite, we want to go to the sun. If we just somehow try to come in this way, where it pushes to that point, and it can exit in using that same manifold to come to this sun orbit, like this. We can use these manifolds as a highways to go from one planet gravitation to another planet gravitations. And what is stable and unstable, say these directions, where in the y direction and z direction, those are called stable manifolds, which will push the any satellites towards that point. And these one are unstable manifolds in x direction. Yeah, the physical picture, the saddle points or the stable points, these are y-axis and z-axis, as I said. And yeah, as Nirav explained, the eigenvalues, if they are positive, they are stable. Negative, they are stable. Positive, they will drift away. And if they are imaginary values, they are periodically, neutrally stable. We can say like that. And the saddle points are at this exact Lagrange point. You can imagine like this. Yeah. If you look from the x-axis, uh, this is the x-axis. You can see that gravitation's pulling, so any object will there, it will go down, will pulled away. But if you see from the y-axis, in the context of y-axis, it will look like this. It will come to that point, never drift away. So the saddle points are this one, unstable one. there is a small disturbances too, it will exponentially get away from this, drift away from this. And the topographical bowls, these are existed at the L4 and L5 Lagrange points. At these points, there is no positive or negative eigenvalues. It is only imaginary eigenvalues. What imaginary eigenvalues? It is like a not even I mean attracting everything, not even repelling everything. So this will become a topographical bowls, just like a bowl oscillating inside of that. Any material goes into these points, it will stay there, oscillating there, and it can trap the like Trojan asteroids and other materials and non-linear frequencies. This as Nirav has explained, where I will explain using axis. We know this because in the y-axis it is attracting and in the x-axis it is repelling. Whenever we create an orbit, like say up to some diameter of orbit, because you know what happens in the z direction and y direction, the frequencies are different. The frequency of oscillating in this way and in the z direction is different. In that case, what happens if you keep a random diameter for that, it will create something like a rings, not a proper orbit. So scientist has to come up with a particular diameter of that orbit, so it matches with the both frequencies. You know, if the amplitude increases, the frequency decreases. So like that, at particular amplitude, the frequency will match, and that will create an orbit in the z and y directions, facing towards the sun, like in this direction. Yeah, in the z and y direction. So that frequency is matching in the xy direction and z direction. The Jacobi integral. Yeah. From the equations of motion, he said that the gravity and centrifugal forces they are conserved, but the Coriolis force was not. This is a different one, because it is generated because of we are considering rotating frame. So when we try to calculate this, for finding out this, we cannot conserve the Coriolis, so it will tends to the chaotic one. So that's why the Jacobi integral, this is a mathematical trick that usually cancels these both two. Can show that. These both are the equations of motions what the Yash has found, like x double dot minus 2 y dot is equals to dou u by dou x, and y. These are the equations of motion we got in the x direction, y direction, and z direction. There is no Coriolis force in the z direction. These two are the Coriolis forces, and the centrifugal and gravitational are potentials included in these two equations. These three equations. When we multiply the velocity, like x dot here and y dot here and z dot here, if we multiply this, what happens? That x dot minus 2 y dot x dot is equals to dou u by dou x dot. It will somehow become like this, and we add 3 of these equations. So because it is a minus here and plus here, it will cancel away in the entire equations. Finally, what we get something like this: x double dot is equals to 2 of dou u by dou x. I'm just writing for one equations. Here, this x dot plus x double dot is nothing but the differentiation of the time differentiation of the velocity x dot square, both are equal. So this is a velocity, and we can write that as a, you can write that of v square d by dt, like this. So here we got the velocity, and here we have the potential, and finally we can write that as v square is equals to tau uh, 2 u of minus c. Here minus signs becomes because of the orbital convection. Here we integrate this. After this one and this one, we integrate both. We get this of v square is equal to 2u, and this off will be there, that will be sent this side, and it adds to the constant, and because of the orbital mechanics, the sign convention, it is made it as a minus. So finally this is the equations we got. And here we can clearly observe that when we are in a space at instant of time, this one remains the same, potential will remain constant. See, this is a v square, it cannot be negative, it should be positive. And this is nothing but a Jacobi constant. We give it as a Jacobi constant, where we use this one. This is the velocity of a spacecraft. This is a exact point what is the potential, and this is the constant defined by the speed of that spacecraft. Say if I increase the velocity of the spacecraft, this doesn't change, but this should decrease, because it is a negative. It should not be, overall equation should not be negative. So here it says this is higher than the this one, like 2u should be greater than c. By this we can clearly figure out at what point in the space we can, how much of velocity we can give to pass through that one. Yeah, using this equation we can map the space. See, at the some regions, say this is a planet, it has some potential up to here, and here there is a different potential. Here what is this, the 2u is less than c, here the 2u is greater than c. So basically the spacecraft cannot go away from this wall. This will create like a wall contained zone where the spacecraft should remain inside of that one. If we want to our spacecraft go away from this zero velocity line, this is a zero velocity line, away from this, we just have to increase the velocity here, velocity of the spacecraft. When we increase the velocity of spacecraft, it will decrease the c value, and potentially giving the positive value for this one. So at that place this velocity curve will expand. What happens if it expands? This is sun, this is earth. If we increase the velocity, the spacecraft boundaries where the zero velocity curves will be there. If we increase the velocity, it will expand, and the both will touch each other, and it will open a gate to pass through between them. Using this method, this equation and all, we can jump from one planet to another planet. Yeah, this is the same thing. Like if we increase the velocity, it will open the gate. That too happens at exactly the L1 points. Even though we all have these equations and all, we still have the, I mean, in the 18th century, 19th century, we found out that this is not a reality. Where when we go there, even the search said, even the small disturbance in the halo orbit, it will create a disturbance, and it will exponentially increase that one. So they come up with an idea called the chaos theory. People say that chaos theory is a random one, but actually in the entire world, everything should be followed by the law of physics. It cannot be random. It should follow the law of physics. But the thing is, the initial condition, even a small variation, it will change eventually it will change change its value after some time. So they have introduced this chaos theory. Chaos theory, it was arised from the three body problem, because they have found that this is a chaos theory cannot be solved. So they have their own theories, and they made different kind of explanations and all. Because why this is very sensitive, extremely sensitive to the initial conditions, uh, and it gets highly predictable for the longer times. To explain this, in the 1960s, a scientist has termed the metaphorical theory, that is butterfly effect. He said that if a butterfly in the Brazil just flaps its wings, it can create a tornado or cyclone in the Texas. Just a small variation at some far away will create the disturbances in the atmosphere, can lead to some extremely catastrophic things in some other places. He came to this because of the weather content. When he was calculating the weather predictions for the long time, he has changed out the weather inputs just like the fraction of 1000 or 5000 something. But it is a very small value, he didn't expect that. But when he calculated for after just a week, it has came out completely different weather predictions. So this has came to, he has published a theory to metaphorically represent that butterfly effect. Like he said that even the exhale of the astronaut, it creates a very small disturbance, but as the time grows, this one exponentially grows, and overall the final time, his prediction is collapsed. So yeah, if the system is chaotic, but how are we predicting that? We are predicting still many things. We are predicting the solar eclipse, and when the this lunar full moon and half moon comes. How we are doing this? It comes to the Lyapunov time. When he's studying about this chaotic, he thought like, okay, how long we can predict this one. He took the same equations from the state space from what Nira have derived. He simplified that to finally represent disturbances, like disturbance will be like it related to exponentially it grows. This this is the time, and this lambda what is taken, this is the positive eigenvalue of the state space representation what the Nira have shown. So he took that one, and he finally simplified it to like what is the time is the inverse of this exact lambda value. Whenever this lambda is higher, this time is lower. But for the solar system, all the planets have the this lambda value very less. What is that lambda value? It says how steep the that unstable manifold at that particular time is. If the steepness is too high, this drift will be very high. If the steepness is too low, it is very low. Like that, this lambda value can be determined. With that, he said that uh, yeah, for even the weathers, this lambda value is too high, extremely high. We can predict weather for only up to a week, not more than that. Yeah. Why this Lyapunov time is important for us? Because for planets and all, we using this very small lambda value, we can predict the behavior of the planets up to for millions of years. That's how we can able to say. But when you go to the Lagrange points, what happens near the Lagrange points, this lambda value increases very exponentially, very too high, near to those points. So what makes this one? This one makes the time decreases too small. It goes up to just like 2 or 3 weeks, like up to 23 days. So after the 23 days, you have to do calculations again, and you have to decide how much stress to be given to maintain your satellite. So that's why this time is very important for us. Yeah, finally, Euler and Lagrange have successfully gave us the coordinates for 5 points, and how we can perform the orbits and all. But chaos theory and Lyapunov tells us like how to maintain them at there. It is mathematically analyzed if the local space allows us to actually survive there. So it is important to consider that one for maintaining the orbits there. Yeah. So others will continue from here.
Uh, After all the theoretical study that we have explained, Now I'll explain how this theory came into the picture from history and the real world application. First, in 19th century, in 1830s, the Hamilton gave Hamilton mechanics, in which we study all the system based on the energy. We started studying based on energy, not through the forces, and this helped in our analysis of the system in better way. Second, in 1840s, Jacobi gave Jacobi integral, in which he introduced a constant conservating term even in rotating frame, which is C is equal to, here U is the potential and V is the velocity. In 1890s, Poincare studied the three-body problem deeply and found that the no closed form solution exists. Now, as we know that after World War II, the Cold War began between Soviet and USA, and space war between them was also part of the Cold War. So during the early phase of the space war between Soviet and NASA, in scientists like George W. Hill gave linear theory, which evolved to current CR3BP equations. In 1850s, mathematician formalized Routh mass criterion, which which was explained previously, that to have stability, to move stability in a stable way around L4 L5 Lagrange points, the mass ratio should be less than 0.0385. And in 1916, Robert Farquhar gave the concept of halo orbit first time. Now, after that, in 1990s 2000, the concept of space highways came first. Like, if we want to do, if we like, do you know Voyager space mission, in which they were intended to go beyond solar system. In this mission, fuel is very critical thing, and we don't want to utilize it as early as possible. So it was planned that to move them from Earth to the beyond Pluto. For that movement, instead of using fuel, we can use other planets or celestial body gravity, and this path that spacecraft use with the help of other celestial body gravity, it is called space highways. The two main scientists to propose that were Kathleen Howell and Edward Will. Now, whatever we have studied in this PPT, it was based on Newton gravitation theory, but in 1915, Einstein gave general relativity, in which we know that gravitation is not a field of force, but is a curvature of space-time. So whatever we studied, is it wrong or true? So scientists did that. They added a correction term, like you can see the based from Newton mechanics, the total potential total energy is V graph plus half omega square r square, total potential function. So they added a correction term delta U by c square, where c is the velocity of light, and the delta U by c square incorporate relativistic mass variations. And this total term U Newton plus delta U by c square became Einstein's potential function, which is U relative. So to gather the new set of Lagrange points, we have to solve for delta U relative greater than 0. And after doing this, scientists found that considering position of L1 from Earth, it is 1.5 billion meters. So after doing all the calculation, they found that the new position due to Einstein relativistic function was just 12 meter ahead from its initial position. So as you can see, 12 meter per 1.5 billion meter, very small error. So we found that the Einstein point shift, that's true. But for low gravity system like Earth and Sun, Earth and Moon, it doesn't matter, because 99.99% Newton is correct. So when Einstein actually matter? His theory is mainly used when very high gravity forces are under the work. For example, considering the two supermassive black holes orbiting each other or neutron stars, so their L1, L2 points shift very massively because very high curvature of space-time fabric. Second is, as we know that if mu less than 0.0385, we have a stable motion around at L4 and L5, but this theory also fails. Even if we have mu less than 0.0385, but in high gravity system, due to the continuous emission of gravitation wave, the energy drains from the system. Now the limits of CR3BP. So we study the CR3BP case by taking some assumptions. So first assumption was that Earth orbit around the sun was circular. Second is in universe we are only considering Earth spacecraft and sun's gravitational field. We are assuming all other things don't exist. Third was that the gravity is the only force acting on the spacecraft. So if we directly upload the CR3PP code or system into the spacecraft, in which it will move from its Lagrange points and will lost in the deep space. So like for considering the first assumption, like circular orbit of Earth around Sun, as per the Kepler's first law, the orbit or any orbit is ellipse. So for Earth orbit, eccentricity is 0.0167. So when Yash explained the normalization of radius or distance between Earth and Sun, here we cannot do that because it is not circular. So that normalization part fails. Also because the distance between Earth and Sun varying, the L1 and L2 points are like pulsating inward and outward. And this problem is not known as CR3PP, it's known as elliptical restricted three-body problem. Now, second assumption was that the Sun, Earth and spacecraft gravity only exists. So this assumption also feels like consider moon mass. Moon's mass is 1/81 mass of Earth, which is not less, which is very much high. So it will perturb the Lagrange points. Also, Jupiter, even though Jupiter is very far from Earth, but its mass is very high. So it will also have effect on the Lagrange points, even though it's small, but it's noticeable. So thus, what scientists do that they use ephemeris model, in which in this model the gravitational force of all 8 planets, Sun and Earth, Sun and Moon, all of the gravitational force are calculated on real time basis, and the perturbations on the Lagrange points and the effect on the Lagrange points and the position of Lagrange points are calculated on the real time basis. And the final assumption that only gravitational force exists, this is also false, that we have sun exerts solar radiation. This solar radiation, as we know that electromagnetic radiation exerts momentum and force, even though they don't have mass. So continuous solar radiation pressure on the spacecraft will result in the continuous force. For example, the JWST problem. In JWST, there is a massive disk which is about the size of tennis field. So when solar radiation exerts force on them, it tend to topple on its center of mass. So what scientists did, in order to prevent that topple, they built a mechanical trim flap to prevent the toppling. Now Shubham will explain next.
So hello everyone. So let's continue with the how I will be explaining how ISRO and NASA uses the Lagrange L1 and L2 Lagrange points. Now before going to that, first see why do we go under so much of headache and mathematical under mathematical complexities to use these points. Because in LEO, the spacecraft faces challenges like firstly, in the typical time period in the LEO orbit is 90 minutes, meaning that the spacecraft will revolve around the Earth 16 times in a day. So as the spacecraft plunges in the shadows of the Earth 16 times, it will undergo thermal shocks. The materials will undergo severe contraction and expansion. That is the first reason. Next, eclipse. So during this, when the spacecraft revolves, the Earth will continuously come in between the line of sight of the spacecraft and the Sun. This is another reason. And third is the radio noise. The Earth actually is continuously interfering with its radio frequencies, the cell towers it has with the spacecraft. So the Lagrange points offers advantage with these three. How? First, you get zero eclipses on this point. Then it offers a stable thermal environment for the spacecraft, and next there is a 24/7 communication without any break. So the L1 Lagrange point is the flagship mission of ISRO's Aditya L1 and also NASA's SOHO. Now this point also offers a tactical advantage. This point is actually located 1.5 million kilometers from the Earth. So whenever a solar radiation, solar flare or solar wind comes towards the Earth's surface, then it reaches the L1 point 1 hour before it reaches the Earth. So in a way, this point acts as a weather buoy. It gives the warning of the massive coronal mass ejection from the Earth 1 hour before to the Earth, so that the power grids and the satellites could not be damaged due to the flares. Next is the L2 point. Now the L2 point is located again upon 1.5 million kilometer downstream of the Earth. That is here, and this point is mainly used to explore or discover the deep space. That is the old galaxies and all, and those galaxies are observed by studying the infrared rays. And I'll talk more on this in the further slides. So now we'll see how in real world these points are used by the ISRO and NASA. So first is the ISRO's case study. I just explained why LEO and all are not used. So let's go how we use this point. Now, first of all, the Aditya L1 is not parked stationary exactly at the point. It is the flight mechanics engineer have explored the imaginary eigenvalues and they have injected the spacecraft into a 3D nonlinear halo orbit. Now, even though when it is injected, there is also a natural instability due to the positive lambda r. So due to this instability, the spacecraft has to perform precise orbital corrective maneuvers on a weekly basis. And to do so, it uses its thrusters. So that's a very key part. If the thrusters fail, then it won't be able to orbit around the L1 point. Next is the L2 point, where our James Webb Space Telescope is parked. And now, as I said, this point is used to explore the deep space. Now, the infrared sensors that studies the infrared rays coming from the deep space has to actually perform at very critically low temperatures of about 40 kelvins. So now to maintain this operational cryogenic temperature, it has to be shielded from the solar radiations from the radiations of the other bodies. So now this Lagrange point offers an advantage that from here now from this point, actually the position of Sun, Earth and Moon is relatively fixed. It does not change with time. So the JWST uses a 5-layer plankton solar shield, to shield the radiation from these 3 bodies of the infrared sensors, so that it can remain at the operational cryogenic temperatures to study those infrared rays. And there is also a drawback of this. The drawback is the solar radiation pressure that it has to overcome. Now this shield is the size of a tennis court. So you can imagine how massive this shield would be and how much solar radiation pressure it has to overcome. So to overcome this pressure, the JWST uses the reaction wheels, and these reaction wheels actually rotate to overcome the force that is trying to push the JWST away from the L2 point. And also there is also a natural instability of this point due to the positive lambda r. So now to overcome both these forces There's also a finite amount of propellant is being used by the JWST that limits the life cycle of our JWST telescope. Now there's another point, L3. Now this is the hidden point, that is 1 astronomical unit from Earth at directly opposite to the Earth. So this point remains unexplored. I mean, nobody has even raised a mission to go to that point. So before that, there was also a sci-fi myth for decades that people believed that there is a counter Earth located at that point. But now we know that it is not. There is no such thing over there, because if there would have been such thing, then due to the n-body perturbations, that Earth would have been perturbed from its position, and we would have been able to see after a certain time. So this is just a myth. So now, why haven't we yet explored that point? Why don't we use that point? That is mainly because of the three reasons. The first one is the blackout. Now the sun acts as a radio frequency jammer. So even if we put a spacecraft there, then it won't be able to communicate or send information to the Earth surface. Now the next one is the fuel penalty. Now to reach to that point, first with whatever velocity the Earth from the Earth, escape velocity the aircraft will launch, then it has to dump all that dump the major of its orbital velocity. That requires a very high amount of fuel. So there is a fuel penalty. Now the third one is the instability. As my L1 and L2 points were unstable, L3 point is also unstable. So we need station keeping commands for the spacecraft to keep there. So for those commands to send, we need to send the signals. That is again not possible to do the blackout. Now further, Somik will continue and tell about the L3 and L4 Lagrange points.
Hello everyone. So after all the physics and mathematics, let's look in some of the case studies again. So generally orbital mechanics was used to travel from one point to another, but today we are looking into park and stay in some of the stable positions in space for future deep space missions. So two of such stable points are the L4 and L5 points. So unlike L1, L2 and L3, L4 and L5 are very stable points. So I'll just quickly show the diagram of L4 and L3 points. Like for a Sun-Earth system, the L4 and L5 points are actually 60 degrees ahead and behind the Earth. So this is the L4 and this is the L5 points. So these points are mathematically very stable. So this actually summarizes what I have said here, and so why do we need to go to L4 and L5? In cases of Sun-Earth system, the L4 and L5 points are very empty. But in case of the Sun and Jupiter system, due to the very high gravitational field of Jupiter, those points are actually filled with asteroids. So like they have been accumulating there for over millions and billions of years. So approximately there are around 12,000 such debris stuck there and trapped. So they are actually called the Trojan asteroids. And so NASA has already sent a mission in 2021, the Lucy mission, which is actually traveling to the L4 and L5 points of Jupiter to explore those asteroids. And why are those asteroids very special? This is because as those points are very stable, the asteroids are trapped from the beginning of our universe. As a result, they contain many fossils and like the history of our space. So for the Earth system, the L4 and L5 points are very valuable in terms of our future space missions. For the Sun-Earth system, the L4 and L5 points can be used as the satellite relays for communication in case of the Mars, like for in case of Mars colonies, and if we try to put humanity habitats into the space, like deep space, we'll be using the Earth Moon L4 and L5 points. So like the massive million tons cylinders, like the O'Neill cylinders, can be placed at those points, which would require very less station keeping maneuvers and can be used for human like explorations of space, unlike the ISS, which is revolving. Then so currently the problem is not with the mathematical estimation of those points. They are very accurate in calculation, but the problem comes with the hardware. So in case of a very minor failure in the hardware, those disturbances can actually propagate and create more problems and force the spacecrafts or any of the objects in those points to fly off at very large distances or get lost in deeper space. And so one of such cases happened at the Soho disaster, which was actually a ESA NASA program. In this, due to a software problem, the thrust for keeping the spacecraft at the L1 point was not met. As a result, the continuous thrust was not given. So it actually fled off from its initial point into some deeper space. Then after months of sending blind signals from the telescope at Arecibo from Puerto Rico, it was finally recovered from those position and then again put back into the stable, again brought back into the stable uphill. Then so here comes one of the mysteries. Then are the stable machines empty or they are minefields for the Earth Moon system? So in 1956, Polish astronomer claimed to observe massive clouds of small asteroids in the L4 L5 points. So for many decades it was not it was not confirmed about those things. Then in 2018, this was finally proved using polarization filters that atmospheric dust is there. So the problem, like one of the problems that would arise is if we want to place our spacecrafts and any other habitats in those places, would those sands and small meteors affect those, hit those spacecraft and make them uninhabitable? And then this interplanetary superhighway concept was explained by Bharat earlier, so I don't need to focus on this much. Just there are stable and unstable manifolds here, so they can just be used to travel within. They can be used for interplanetary traveling. And then the second mystery comes with the computational abyss. Now there are n bodies in the solar system, so there are not very clear Lagrange points and superhighways that was defined. As a result, they form a net of those superhighways, as a result of which a small error can also would be very fatal in those cases, because all other gravitational forces would also impact that. So it as can be seen from here, an error of around 10 to the power 5 meters per second can mean the difference smoothly arriving at Mars or being thrown out of the solar system easily. So the goal, current research is here supercomputers are using machine learning to and using brute force methods to estimate those paths very clearly in space, so that they can be further used for interplanetary travel. And finally, the Yarkovsky betrayal. In this, already it can be it was already seen that L4 and L5 are mathematical stable points, but it has been seen that some asteroids have moved out of those points. This is because asteroids rotate in those points. As a result, the sun, the heating of the surface, as a result of heating, the asteroid releases thermal photons, and these photons actually act as thrusters, like the thrusters in electric and solar propulsion. As a result, those asteroids continuously try to move. and those eigenvalues, the stable eigenvalues at those points are disturbed, and the Jacobi constant uh, slowly changes, and ultimately the asteroids escape the L4 and L5 positions. So predicting when these asteroids would finally come out of those points and pass near the Earth, or impact the Earth, this has been a very intense research for our own defense. So in conclusion, I would like to say that these Lagrange points are not just mathematical points anymore. They are the locations where we would like to park and like to establish our habitats in future for deep space missions and also explorations in space. Next, Gaurav will be continuing.
Here I'll be presenting the final part of our POT, and we already have been presented more than 85 slides, so I will bring all this in together in my part. So first, the hovering paradox and the CR3VV problem. So in absolute inertial frame, so a object cannot stay stationary in space. So either it has to orbit around a heavier object, like Earth is orbiting around Sun, or it has to pull down towards that heavier object. So now if we consider the rotating frame, so what happens? Earth and Sun are both stationary in that frame, and the frame is itself moving. And now if we introduce a small spacecraft having negligible mass compared to the Sun and the Earth, so what will happen? So there will be some particular positions where the velocity of the spacecraft will be 0. So it will create illusion that the spacecraft is hovering on those particular points. So this is the concept of hovering, and obviously we are considering the rotating frame. So we have to consider the Coriolis force along with gravitational force and centrifugal force. And next, I will talk about mathematical equations. That part already has been explained by Yash. And now if we consider the three forces, Coriolis force, gravitational force and centrifugal force, then from mechanics we got that equation of effective potential. So the first term comes from the centrifugal force, and the second term comes from the heaviest object, that is Sun in our Sun-Earth system, and the last term comes from the contribution of the second object, that is the Earth. So basically, the spacecraft we have introduced having negligible mass, if the velocity of the spacecraft and the acceleration are proportional to that gradient of that effective potential function. So if we impose that the velocity and the acceleration is 0 of that spacecraft, then we got that the gradient of that effective potential function is 0. So from there we will actually find 5 points where the velocity and the acceleration of the spacecraft is 0. So like the spacecraft is hovering on those 5 points. So these points are known as Lagrange points and named as L1, L2, L3, L4 and L5. And next I'll talk about first L1, L2 and L3 points. So these are basically collinear points. They are collinear to each other and they are collinear to Sun and Earth also. And from the space-time curvature, that L1, L2 and L3 points are kind of saddle points. So, and if we do the state space analysis, and if we calculate that characteristic equation and then the eigenvalues that are nothing but the poles of that system, then we will find that the poles are positive. That means that these equilibrium points are highly unstable points. So here basically what happens is small perturbation, like the breathing of astronaut can create a small velocity increase. So the velocity will increase from 0 to a small value, and that will create a Coriolis force that will increase from 0 to a some value. And we know that the Coriolis force acting in sideways direction in rotating frame. So because of that, this will create a huge drift in that spacecraft. So because of that, the spacecraft will be drifted from that point. So the L1, L2 and L3 points are highly unstable point. And next I'll talk about L4 and L5 points. So from that image, so there are L4 and L5 points are there located, and L1 point is actually here, L2 is here and L3 is here. And now if we analyze this through Raoult mass criterion, so we'll find that for a small mass ratio, the L4 and L5 point are having imaginary roots. That means these points are unconditionally stable, means dynamically stable. And also these points are not exactly a point. These are kind of a stable basins. So basically these points can, or this region can trap spacecraft, or it can trap asteroid. So we have one example, Jupiter actually traps thousands of asteroids in its L4 and L5 points. And now if we calculate the Jacobi constant, what Bharat has calculated. So then we can find zero velocity curvature, higher velocity is zero. That means the kinetic energy is zero. So these curvature are actually closed loop. And for a particular C, we have a particular curvature. And if a spacecraft is trapped in between that loop, so it can't go beyond that curvature. So, but we can manipulate or we can modify the C, and C actually depends on the perturbation that actually is the thruster of our spacecraft. So we can manipulate C from the thruster, and C will manipulate the that zero velocity curvature, and accordingly the spacecraft can move from L4 point to L1 point. So that actually this is actually one zero velocity curvature that has one particular C value, and we can take another curvature that has another particular C value. So this is how the spacecraft actually moves from L4 to L1, and in that rotating frame also. And next, I will talk about some flaws and some perturbation that others already has been explained. So some flaws we have given that are the orbit of the Earth is not circular; it's elliptical, and we can't ignore the gravitational force of the moon. And because of that, the problem doesn't remain a three-body problem; it becomes an in-body chaos. And obviously, Einstein relativity shift we have to consider. And perturbation means obviously in space we have solar radiation that actually creates pressure difference. And if a spacecraft having a sun shield, because of that shield, this shield will act as a solar cell. So because of radiation there will be pressure difference, and obviously because of that there will be huge drift in that location of the spacecraft. And obviously we have some modern solution for that also. And next, I'll talk about surviving at L1 and L2 point. So first thing, why L1 and L2 point? This is an unstable point, but L1 point is actually located between Sun and Earth. So from here we can observe the Sun very carefully. So we have one example, Aditya L1, that already has been explained by Gaurav sir and Nirav. And also in L2 point, actually this point is located in one side of Earth and Sun both. So from there, if we place a spacecraft here, so we need only one thermal shield, so that can protect the telescope. So we have one example, JWST. So these are the reason why L1 and L2 points become our point of interest. And now these points are unstable points. So to survive a spacecraft on those points, so we have to use a lot of control effects, and here concept of halo orbit comes into the picture. So we have to use a lot of thruster adjustment such that the whole system actually will become a dynamically stable system. That means it will have imaginary eigenvalues. And halo orbit is a 3D orbit. Here the spacecraft will be orbiting the L1 and L2 point. It is not. It won't stay at that point actually. So hovering means it will orbit around those L1 and L2 points, and it will have a oscillation motion also. So that's why the halo orbit is a 3D orbit, and that is actually the halo orbit. So I have shown, and this is the L2 point. So the spacecraft is not actually staying at that point. It is actually orbiting around that point and having an oscillation motion also. And next one example I will tell. So that is SOHO in 1998, that already have been explained by Shomik. So the spacecraft was able to reach at that L1 point, but it was not able to survive at that point because a small perturbation caused a huge drift, and it didn't have proper thruster adjustment system, so it went to deep space. So next to unsolved problem, so one that interplanetary transport network has been explained by Bharat. So by using that system, we can use we can use this system in spacecraft transportation. So we know that L1 and L2 point causes these are very unstable point, and a small perturbation causes a huge drift. So we can use perturbation from the gravity of the moon and any other planet like Mars. So from there we can use a drift. So that means the spacecraft will move in a particular direction. So basically here we don't need to use thruster. So actually with zero fuel we can move the spacecraft from one place to another place. And the next one mystery that already have been explained by Somik. So in Earth Moon system, in L4 and L5 points, so these are stable points. So there are a lot of asteroid dust. These are actually trapped here. But these dust actually are consuming thermal energy for years.
So, and this thermal energy actually creating thermal thrust, microscopic thermal thrust, and because of that, these dust are actually able to escape that stability region or that stability basin. So, this concept also we can use to clear those region, and we can put our own spacecraft. That already has been explained by Shomik. And next, in one slide, so to execute a mission in modern era, so first thing we have to consider, we have to model the CR3V system carefully, and obviously we have to consider the n-body problems and all these things, the gravitational force coming from the moon and any other planets like Mars, all these things, and obviously then stability theory will come into the picture. From here we will calculate the eigenvalues of the particular locations L1, L2, L3, L4, and all these things, and then to survive or to keep a spacecraft around that unstable equilibrium point L1 and L2. So we have to consider the periodic orbit theory. So I have told halo orbit, and obviously to transport a spacecraft we have to consider the transport system that I have told, and obviously the system will become complex in mathematics, so we have to use modern numerical method like shooting method. Obviously we have to use HPC systems like supercomputers and other things, and at the end of the day the control theory will come into the picture, and which will actually helps to adjust the thruster, and because of that the spacecraft will be able to adjust the change in velocity. So because of that it will be it will be staying in those region around L1 and L2 points. So control theory is the most important here. So next in the concluding line I'd like to read from that PPT. So hovering in deep space is a mathematical impossibility, but by exploiting the very instability that forbids it, engineers have turned the solar system's deadliest saddle point into humanity's greatest observatories. So that's all from us. Thank you.
Okay, in the interest of time, we will try to have very minimal questions because there are two teams in a great hurry. So first of all the way from the time you talked about WingRock, I think all the presentations that your team has given, you have done a really good study of not only the basics but also the real applications and also what is in the future. And today also that came out really well. Many a times when you start a topic, it feels like, why are they covering this? It's irrelevant. But soon we can see the connect and can identify the need for each of the topics that everybody's presented, right from the introduction by Gaurav to the conclusion by Gaurav. So I think that covered the entire spectrum. So I really loved that. Just a few remarks. Anyway, it will not be useful for this particular course, but for the future, again, when you continue to use AI, you see there are still a few bloopers. For example, Gaurav, when you started, you talked about the L4 and L5 being on equilateral triangles. If you see the 60-degree where it is, it's not the right way, whereas a few others showed it in the correct way.
That was more like representative. That's
correct, right. So you should identify those things, and once you identify, you should make attempts to kind of correct it. So I just request that for you whenever you happen to use these things, because I'm sure you'll definitely use it for many other not courses but in your careers as well. So keep these things in mind in terms of the takeaways from this particular course. One generic question, because we're talking about the three-body problem and potential to extend it to the n-body problem, and in fact the need to do that, which many of you covered very convincingly. I also want to see from, let's say, a two-body massive bodies and a third body to be put up at one of these Lagrange points. Between the three stable points, unstable points, and the two stable points, L4 and L5, there are advantages and disadvantages. Okay, and of course, mission requirements, all those things will come into place in terms of deciding that. But in terms of purely from a point of view of the propellant that is to be expended, or the propellant weight fraction or volume fraction that you need to take. In one case, for the unstable orbits, it will essentially get into halo orbits, so you have to repeatedly keep firing your thruster. So whatever the period of the interest is, you'll have to expend fuel in that way. Whereas when you're going to L4 and L5, the distances are much larger. Except of course, you leave out the point behind the sun. Well, let's talk only of L1 and L2 compared to L4 and L5. So L4 and L5 much farther compared to L1 and L2. These are just about 1.5 million kilometers, whereas there if you take in terms of the equilateral triangle, you're essentially from the Earth the same as one astronomical unit, which is 150 million, which is 100 times. So whereas it is stable, so therefore you may not have to repeatedly fire your thrusters, but you will have to expend a lot of propellant going to L4 or L5 itself. So in terms of the comparison, just offhand, can you think of which would be a more effective or efficient thing, depending on the period for which you want the whatever the application to be?
Based on this logic, the L1 and L2 will be a more efficient because, first of all, we
Despite
don't
the requirement to keep repeatedly firing your thrusters for unstable halo orbits.
Still it's a good because to reach up to L4 and L5, we required a bigger rocket. We required that much fuel to just reach to L4 and L5. But compared to that, to get into L1 and L2 orbit, we still required a smaller amount of propellant, and by using our optimal theory and converting to these three body problem, we can still get a smaller propellant to use a smaller propellant to just get into the halo orbit or any of the orbit to around L1 and L2.
So, I mean, I have lots of technical questions, but I'll avoid them. I just wanted to come to you, Yash, because you brought in that unique perspective in the previous presentation as well as this to cover certain things from an Indian perspective into this. Whether it's from an Indian perspective or Chinese or Greek or whatever of these perspectives, we should remember, especially the ones which have come from Bharat, the way we distinguish people is not just as this person is a scientist, this person is a poet. So typically whoever is a poet will also be a scientist, whoever is a scientist will also be a poet. So many of these things, when they are covered in terms of let's say a parable or a story or whatever, it's highly loaded, okay? And so essentially what they're trying to do is to please a much larger audience, whereas you're also trying to use certain cryptographic ways of encoding certain deep truths into it. So if you are interested in this and anybody else who is interested in this, I would like you to give you one important hint. In Sanskrit, almost all the nouns are named based on their nature or properties or the work that they do. Okay. For example, if you take apa or jala for water, it's all based on certain characteristics of water. So going from the same thing, if you look at Vishwamitra, Trishanku, all these people that you mentioned, from a story perspective, it looks very good. It's great for kids and also as a memory mnemonic. But if you start going deeply into it, what is Vishwa, what is Mitra, and then try to combine those two in a much more heuristic sense, as rather than as a person. This is not to belittle that these may not be historic persons or whatever. That's besides the point. But the very fact that you're using certain names, certain terms, there you can go further deeper into it, dig deeper into it in order to understand from a much deeper perspective. This also goes with the other question that you asked me about Vaimanika Shastra. A lot of people just decried based on Subbaraya Shastri, Anikel's work, which was only one small part of the entire Vaimanika Shastra that is there in the spread out in many different places, whatever is remaining after whatever was burnt in Nalanda library fire. But even whatever is little is remaining, there are parts of it which people can read and make fun of it. Like for example, there are portions, as I told you the other day, where they say that the propellant can be made out of human hair and nails. That doesn't mean it's actually the human hair and the nail. The same word which is used for nail and hair can be used for certain materials and certain chemicals based on the properties that particular noun that is used for the nail or for the hair that is included there. So you have to go a little deeper in all of these understandings. So I'm glad you have made that beginning towards that, because this is a massive area in which we can identify a lot of different possibilities, not purely from the point of view of saying that we have done this before, but in the taking it to the future in terms of what is the carryover for current projects or future projects, how we can probably utilize some of those conceptual ideas by appropriately tailoring it to the new requirements or new engineering that is required. So from that perspective, individually, I'd like to really congratulate you. But once again, as a team, you've done a fantastic job. Though you've been taking a lot of time, I can also see that some of these topics are kind of loaded topics. Unfortunately, you should have done this presentation for the 13th question first, and everybody else should have followed, but we had the Garuda and right wing present even before you. Those are very complicated topics, the 5th and the 6th in this whole list. And a lot of that, if now revisited in the background of the information, the introduction that you have given, if we go back and watch those videos, we'll see that we can learn much more from them now than without this knowledge that you had shared with us. Okay, so thank you once again. Fantastic job overall throughout the course, and we wish you all a great time in your careers and your life.
Thank you.